Okay guys, apologies I guess are first due up. I guess I forgot to copy the notes packets for you, so this is a little old school. You actually have to take notes in your notebook. Yeah, apologies for that, but I think you'll get by. We're going to move into a more formulaic approach to binomial distributions today, and that is looking at their means and standard deviations. And remember that the binomial random variable is just another random variable. More specifically, it's a discrete random variable, so it has a lot of the same properties as the other discrete random variables we've talked about. So first off, when talking about the mean of our binomial random variable, we are talking about mu sub x. And mu sub x is also the expected value of x, e of x. So if the question is what's the expected value, for this particular scenario, Emily has a probability of success of 0.48 and she's going to take 100 shots. The expected value is really asking how many out of 100 do you expect her to make? And I think there's an obvious answer to this, that she's going to make 48% of the 100 shots. So we would expect her to make 48 shots. So mu sub x is equal to 100 times 0.48, which was the number of shots times the probability of success, which is 48. And in general, when talking about the expected value or the average for the random variable x when it's binomial, it is just NP. So the first formula that we're going to encounter for section 8.1 is the mu sub x equals NP formula. To talk about standard deviation, we needed to know mu sub x because we know that standard deviation is based off of the mean or the average value. So moving to standard deviation, if we consider again that x is the binomial random variable and it is discrete, we can actually generate the probability distribution for x. And it only takes on two values, 0 and 1, a success being 1, a failure being 0, and then we have our p sub I of failure being 1 minus probability of success and success being just p. So for any single observation, we know that mu sub x is really 0 times 1 minus p plus 1 times p. That's that weighted average that we were talking about, and in this case you have no failures and one success, so mu sub x is equal to 0 plus p, which is equal to p. So for n equals 1, np would just be p. So let's go ahead and consider generating the variance for this one observation. So over here I'm going to say, oops, I need a pen. I need the variance of the random variable x. And the variance we know is each of the individual outcomes. We're going to subtract off the expected value, square it, and then multiply it by its probability. So for the first value of 0, I would have 0 minus the expected value p that we just got from over here, squared, times its p sub I value of 1 minus p. And I would add to that the other value of 1 minus the expected value of p, and then square that times its probability, which is p. Okay, from here we're going to do a little simplification. So our variance is going to equal 0 minus p squared is just p squared times 1 minus p. And then plus, I'm just going to keep this as p times 1 minus p squared at this point. And you'll notice that I have some common factors here. Each of these two terms has a p and a 1 minus p. So if I pull out a p times 1 minus p, left inside the parentheses I would have a p from the p squared in the front, plus, and then a 1 minus p for the second term, which in total would give me p times 1 minus p, and then p plus 1 minus p would be p minus p, which is 0, plus 1 is 1, so times 1. So I would have that the variance for x would equal p times 1 minus p. which is pretty cool if you think about it, that the variance of the random variable can be written specifically in terms of the probability of success. That's the probability of success times the probability of failure if n is equal to 1, so for any single trial. So that's pretty important, so we're going to build on that going forward. Okay, so if we know that mu sub x is equal to np and the variance of x is equal to p times 1 minus p for n equals 1, what happens if we expand ourselves to n observations? Because we know in the binomial setting we'll be having a fixed number of observations n. So let's try to do this for n observations. So for n observations. And for n observations, why don't I do something that we did before? Let's generate a new set, and we'll just call it the set z, which happens to be the sum of the outcomes of two random variables x and y. And you'll see why I'm doing this in just a second. So set z would be x sub 1 plus x sub 2 plus x sub 3 plus blah 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 x sub n. It would have all n observations for the random variable x, which means that mu sub z, as we remembered before, would be the sum of all of these averages. So the mu of x sub 1 plus the mu of x sub 2 plus the mu of x sub 3 plus dot 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 plus the mu of x sub n. And for each of these are the expected values for any given outcome, x sub 1, x sub 2, x sub 3. Well, for any given outcome, the probability of success is just p, so np would be just p. So mu sub z would equal p plus p plus p plus p, which, if we did this out for n p's, mu sub z is going to equal np. Which, hey, that makes a lot of sense because that's what we defined earlier, that it doesn't matter how many observations we have. If the probability of success is p, we would expect this new average to just be the number of observations times the probability of success. Now, as a reminder from earlier, remember that if we want to find sigma sub z squared, the variance of z, we know that this is found kind of via the Pythagorean theorem, that this would be the variance of x plus the variance of y. And because these observations are independent observations of each other, I don't need to worry about building in a correlation between them, so there is no two rows sigma x, sigma y that has to be built in here. So my variance of z is really the variance of x1 squared plus the variance of x2 squared plus the variance of x3 squared plus yada 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 plus the variance of x sub n squared. I'm sorry, the variance of x sub n. Well, each of these individual variances, remember from way up here, is just p times 1 minus p. So if I take the variance of z, this is p times 1 minus p plus p times 1 minus p plus p times 1 minus p. And we just keep doing this all the way out for our n observations. So we have n p times 1 minus p's. So our variance for z is n p times 1 minus p's, which we can also write as np times 1 minus p. So to determine the variance for a random variable for n observations, n independent observations, which again by definition the binomial setting has to be independent, that variance would be np times 1 minus p. And again, np is just the expected value, so you're taking the expected value times the probability of failure. And that is going to give you your variance. If you then wanted to talk standard deviation, the standard deviation is just the square root of np times 1 minus p. And if you have one of your formula sheets handy. This is definitely one of the formulas that's given to you. You just have to understand what the heck it's even talking about. This is how you find the standard deviation for a binomial random variable for n observations with probability p success. So in this problem, example number 4, you're told you have a binomial random variable. There are n observations of 70 and the probability of success is 0.55. So do remember that this is b n comma p. So that's not mu sigma. So I want to determine the expected value and the standard deviation for my binomial random variable. So I want to determine mu sub x and I want to determine sigma sub x. So mu sub x should just be np, should be 70 times 0.55, and 70 times 0.55 is 38.5. So mu sub x is equal to 38.5, which again, remember that is also the expected value. And then the standard deviation of x should be the square root of np times 1 minus p. So NP, we just found NP was 38.5. So 38.5 times 1 minus P, so the complement of 0.55 is 0.45. So we are going to find that the standard deviation is going to be the square root of 17.325, so 17.325, which is approximately 4.1623. So there's our expected value and our standard deviation for our binomial random variable. Fairly simple to calculate once you know the formulas. So the next subtopic we're going to talk about is using the normal model to approximate the binomial model. And there's some reason for having this discussion. So the reasoning really goes back to before calculators. Your calculators are super powerful. And as you've seen, you can do binomial PDF and binomial CDF on your calculators and get kind of really easy answers for these binomial problems. But prior to calculators being around, there was a need to kind of standardize the way in which we did problems. Go back to something that we already knew and use that information to move forward. And the best way to do that was to build upon what we knew about the normal model. So when we do a normal approximation of the binomial, we do this, again, pre-calculator wise, to go back to a model that we understood. We didn't have to generate all of these new settings and rules, and in reality you'll see that it gives a fairly decent approximation. So without having to generate this new set of rules, we were able to get decent approximations for what we were looking for. So can we just use this older understanding that we have with this new setting to be able to get this approximation? And if you think about what it is we need for a normal approximation, we need a mean and a standard deviation. And we just went through all this work establishing the mu sub x and the sigma sub x formulas. We can actually use that to make a normal approximation. So that's what we're going to talk about here. Really, there's only a little bit of criteria that is necessary to be able to do a normal approximation of the binomial. And it relates to this statement here. As little n, so as the number of observations becomes large, the binomial n comma p starts to approach n of u comma sigma. And the question is, what's large? So we can answer this question by saying if np is greater than or equal to 10, and if n times 1 minus p is greater than or equal to 10, we consider the binomial, the number of observations large enough to start to approximate the normal distribution for the binomial. So that's what we're going to be using as our justification when doing this approximation for the normal distribution. So we'll do a little check and we'll make sure that we don't have extreme values, and really what this guards against is extremely large and extremely small p-values, really throwing off what the distribution looks like. If you were to look at the distribution for really small p-values and really large p-values, again p being probability of success, you would see that the distribution for a binomial looks nothing like a normal distribution. It kind of looks like this. for the probability of success being small, and then like this for the probability of success being large. Very skewed distributions. We're looking for more of something like this. So when np and n times 1 minus p both are greater than or equal to 10, you get a distribution that looks a little bit more like the normal distribution. So that's what we'll be using going forward. And we'll essentially be saying this, that this normal distribution is going to have a mean of np and a standard deviation of np times 1 minus p. Take the square root of it. That will be our normal approximation of the binomial.